Good morning, class. Even when I'm not there, you can't get away from me. So I recorded a video here to continue our discussion on trigonometry. So let's see if we can get this to work. Well, what we did last time, so have some notes out so you can take some notes this morning. And what we looked at last week was, or not last week, but the last time we met on Monday, we looked at these 6 trig functions. And the main point here is that each one of these functions represents a ratio of 2 sides of a right triangle. And so if I've got a right triangle, and there's my 90 degrees, and I define one of the sides to be some unknown angle theta, then I can come up with a ratio of two of the three sides according to these 6 formulas. But if this is theta right here, then this is going to be what we call the opposite side. It's the side that's directly across from the unknown angle. This is the side that's right next to that, so we call that the adjacent side. And this is the hypotenuse. So there is the hypotenuse. And so for example, if I write the sine of that angle, that is going to be, this represents the number, which would be the side opposite that angle divided by the hypotenuse. Now obviously the sine and the cosine are always going to be less than 1 because the hypotenuse of a right triangle is always larger than either the opposite or the adjacent side. Now what I want us to look at next is, we'll call this Roman numeral 2 in our notes, is I want us to look at the 30 degree and 45 degree triangles, right triangles. And we'll come up with the ratios for these triangles. Let's consider the 45 degree triangle. That means that I've got one right angle, and then the other 2 angles are splitting the remaining 90 degrees. That means then that if I call these sides length 1, I can come up with the hypotenuse using Pythagorean's theorem. Because Pythagorean's theorem says that c squared is a squared plus b squared. C is my hypotenuse. So the length of that hypotenuse is going to be the square of that hypotenuse is 1 squared plus 1 squared. So that's c squared is 1 plus 1. Take the square root of both sides, I get the square root of 2. So this side over here is the square root of 2. So if I start off and I say, okay, sine theta is going to be opposite over hypotenuse. That means for a 45 degree triangle, and we're letting this be theta, the side opposite is 1, and the hypotenuse is the square root of 2. If I rationalize that, I'm going to get root 2 over 2. So what we're saying is that all triangles, all right triangles in the universe that have a 45 degree angle right here, the ratio of the opposite side from the 45 degrees divided by the hypotenuse is always going to be this same ratio. It's not going to change for all triangles with that 45 degrees. If I do cosine theta, that's going to be adjacent over hypotenuse, which is going to be 1 over the square root of 2 again, because my adjacent side is this 1. I rationalize once again, get the same answer, square root of 2 over 2. If I take the tangent function, that's the opposite side divided by the adjacent side. And so that's going to be 1 over 1 or 1. Okay, so keep in mind, these are all equal to, this is the sine of 45 degrees. So this is something that is always true. A right triangle with a 45-degree angle is always going to have that ratio, no matter how large or small the triangle happens to be. The ratio is what will stay the same. That's true. And then, of course, that's true as well. If I pull up the calculator here, hopefully you can see this on the video. If I can find my calculator, there it is. So this is the calculator. Maybe you can see that. If I put myself in degrees mode, I'm in radians, but there I'm in degrees, and I hit 45 and then select tangent, it tells me the answer is 1. Now, if I do 45 and hit sine, it's going to give me this long number here, which obviously is an irrational number. It's a non-repeating, unending decimal. And so basically, if I was using my calculator here, what that's telling me is, let's go back to it. So the sine of 45 degrees is this long number. So sine of 45, according to the calculator, is an irrational number that looks something like this. But if I wanted to get the exact value, what I can do with my answer displayed right here, if I hit square, which is right here, you'll notice that it gives me an answer of 0.5. So what that means then is that if I take the sine of 45 degrees and square it, I got 0.5 exactly. It was not an irrational number. It's exactly 0.5. So if I square root both sides again, basically what I have is I'm back to sine 45 degrees, and I have the square root of 1/2, which is, using the rules of radicals, square root of 1 over the square root of 2, which is 1 over the square root of 2. And then when I rationalize that, I come back to my radical 2 over 2, which is what I knew was going to be true in the first place. So that's just one way that you take your calculator that's giving you an irrational number and how you convert it back into the true exact answer for your problem. Now, the next one that I wanted to look at is the next triangle I want to look at is the 30, 60, 90 triangle. And this triangle, we're going to start to examine this one with the trig functions by first starting with an equilateral triangle. So if it's equilateral, that means that the sides and the angles are all the same. So it's got 3 60-degree angles. And I'm going to let the lengths of the sides all be 2. And you'll see why that is in just a second. What I'm going to do now is I'm going to draw a line that is going to split this side right here. So I'm going to start from this corner and come up here, and I'm going to make that a right angle. What that's going to do, and you probably know this from geometry, but if it's an equilateral triangle, that means this length of 2 is going to be split into 1 and 1. This angle of 60 degrees is now cut in half, and it's now a 30-degree angle. So I have just created a 30, 60, 90 triangle where one of the sides is length 1 and the hypotenuse is length 2. What I'll do is I'll go ahead and redraw that over here. I'm just going to put it right side up like this. So here's my hypotenuse. That's the length 2. There's the right angle. There's my length 1. This is my 60-degree angle. This is my 30-degree angle. So all that I'm missing is the length of this other short side. So using Pythagorean's theorem, I know that c squared is 2 squared. One of the short sides is 1, so that's squared. And so what I get is 4 equals 1 plus the other short side squared. And that takes me to b squared is equal to 3. And square rooting both sides, I get b is square root of 3. So this other short side is the square root of 3. What I can do now is just like I did before. I could write, if I wanted to, and I do, I'm going to write 6 trig functions. And I'm going to write them for 60 degrees. So the sine of 60 degrees is going to be the ratio of the opposite side over the hypotenuse. So across from 60 is square root of 3, and the hypotenuse is 2. So all right triangles in the universe that have a 60-degree angle, if you form a ratio of the length of the opposite side over the hypotenuse, you are always going to get that ratio, no matter how big or small the triangle is. Cosine of 60 degrees is going to be the ratio of adjacent over hypotenuse. That's going to be 1 over 2. There's my adjacent, there's the hypotenuse. And then tangent of 60 degrees is opposite over adjacent. And that would be the square root of 3 over 1, or just the square root of 3. Now I could also come up with the other ones, cosecant of theta, which is the inverse of sine theta. That would be 2 over root 3. And when I rationalize that, I would get 2 root 3 over 3, and so on and so forth. Now you're probably a little bit ahead of me here and realizing that when we come up with these trig functions, we're not going to be using these triangles. We're going to be using the unit circle. Okay, so we'll talk about that in just a minute. But I'm just showing you here where these trig functions come from. They come from these ratios of sides. And so we've just kind of shown that to ourselves by example using these triangles, 30, 60, 90, and the 45, 45, 90 triangle. What I want you to do is take a look at your guided exercise. I think I handed that out to you last time. We did some of it. I think this is what we completed last time. But I want you to turn on the back page because we did not do those. And I'm going to have you do those now. I'm going to zoom in here a bit. And this is the first one on the back page of that guided document. So I'm going to work this one, and then I'm going to let you do the other two. But I've got the 2 triangles that we were just working with here on the back. I'm going to use those to come up with these ratios. So cosine of 30. Well, I come up here and I